Let's compare TensorFlow with other popular machine learning frameworks like PyTorch, Keras, and scikit-learn across various aspects. Ease of use. For TensorFlow offers both high-level and low-level APIs, providing flexibility for different levels of abstraction. While high-level APIs like Keras makes it easy to build and train models with minimal code, low-level APIs offer more control but may require additional effort. PyTorch is known for its simplicity and ease of use, with an intuitive and Pythonic API that facilitates rapid prototyping and experimentation. Its dynamic computation graph approach allows for more flexible and intuitive model development compared to TensorFlow's static computation graph. Keras is a high-level neural networks API that runs on top of TensorFlow, Theano, or Microsoft Cognitive Toolkit (CNTK). It provides a user-friendly interface for building and training neural networks, making it suitable for beginners and experienced developers alike. Scikit-learn is a machine learning library in Python that focuses on traditional machine learning algorithms like classification, regression, clustering, and dimensionality reduction. It offers a simple and consistent API for model training, evaluation, and prediction. Next thing that we'll look around is for performance. With TensorFlow's static computation graph optimization and support for distributed computing make it well suited for training large-scale models on clusters of GPUs or TPUs, leading to high performance and scalability. PyTorch, on the other hand, PyTorch has dynamic computational graph allows for more efficient memory usage and better performance on dynamic architectures or models with variable input sizes. However, it may not scale as well for distributed training compared to TensorFlow. Keras performance depends on the backend engine it is running on, such as TensorFlow or Theano. It can achieve high performance when integrated with TensorFlow, especially for deep learning tasks. Scikit-learn is optimized for traditional machine learning algorithms and may not offer the same level of performance for deep learning tasks as TensorFlow or PyTorch. However, it excels in performance for classical machine learning tasks due to its efficient implementation of algorithms. Next parameter that we'll compare is community and ecosystem. TensorFlow has a large and active community of developers, researchers, and contributors who contribute to its development, share resources, and provide support through forums, tutorials, and documentation. It has a rich ecosystem of libraries, tools, and resources for various machine learning tasks. PyTorch has a rapidly growing community and is widely adopted in the research community, particularly in the fields of computer vision and natural language processing. It has a vibrant ecosystem of libraries and tools, but it may not be as extensive as TensorFlow's ecosystem. Keras benefits from TensorFlow's large community and ecosystem as it tightly integrated with TensorFlow. It also has its own community and resources, including documentation, tutorials, and examples. Scikit-learn has a well-established community and is widely used in academia and industry for classical machine learning tasks. It has a comprehensive ecosystem of algorithms, utilities, and resources for data pre-processing, model evaluation, and model selection. Next parameter is model deployment. With TensorFlow offers tools like TensorFlow Serving and TensorFlow Lite for deploying machine learning models in production environment. TensorFlow Serving allows for a scalable and efficient serving of TensorFlow models, while TensorFlow Lite enables deployment on mobile and embedded devices. PyTorch development options are not as mature as TensorFlow's but are evolving. TensorFlow, PyTorch Mobile and PyTorch JIT just-in-time compilation offer some deployment capabilities, but they may not be as comprehensive as TensorFlow's deployment options. Keras models can be deployed using TensorFlow Serving or TensorFlow Lite, leveraging TensorFlow's deployment infrastructure. Keras also supports deployments on cloud platforms like Google Cloud AI Platform and AWS SageMaker, but Most of them use TensorFlow Lite or TensorFlow Serving. Scikit-learn models can be deployed using various deployment strategies such as web services, containerization, or cloud platforms. However, scikit-learn deployment options may require more manual effort compared to deep learning frameworks like TensorFlow and PyTorch. In summary, each machine learning framework has its own strengths and weaknesses, and the choice of framework depends on factors such as ease of use, performance requirements, community support, and deployment needs. TensorFlow and PyTorch are popular choices for deep learning tasks, while scikit-learn is well suited for traditional machine learning tasks. Keras provides a user-friendly interface for building and training neural networks and is tightly integrated with TensorFlow. Now, what are the strengths and weaknesses of TensorFlow? Here's an overview. So first, scalability. TensorFlow is designed for scalability, allowing developers to train and deploy machine learning models efficiently across various platforms, including CPUs, GPUs, TPUs, and distributed computing environments. It supports distributed computing for training large models on clusters of machines, making it suitable for handling large datasets and complex models. Flexibility. TensorFlow offers both high-level and low-level APIs, providing developers with flexibility to choose the level of abstraction that best suits their needs. High-level APIs like Keras make it easy to build and train models with minimal code, while low-level APIs offer more control over model architecture and training process. Rich ecosystem. TensorFlow has a large and active community of developers, researchers, and contributors who contribute to its development, share resources, and provide support through forums, tutorials, and documentation. It has a rich ecosystem of libraries, tools, and resources for various machine learning tasks, including data preprocessing, model development, training, evaluation, and deployment. Production ready. TensorFlow provides tools and libraries for deploying machine learning models in production environment, such as TensorFlow Serving and TensorFlow Lite. TensorFlow Serving allows for scalable and efficient serving of TensorFlow models, while TensorFlow Lite enables deployment on mobile and embedded systems. Integration with Google products. TensorFlow is developed and maintained by Google, which integrates it with other Google products and services such as Google Cloud Platform (GCP) and Google Colab. This integration provides seamless access to cloud resources, distributed computing, and other Google services for machine learning development and deployment. Now let's look at the weaknesses of TensorFlow. Steep learning curve. TensorFlow can have a steep learning curve, especially for beginners or those new in deep learning and machine learning concepts. It has extensive features and capabilities may overwhelm newcomers, requiring time and effort to learn and master. Complexity. TensorFlow's low-level APIs can be complex and verbose, requiring developers to write more code for certain tasks compared to other frameworks like PyTorch. Building custom models or implementing advanced techniques may require additional effort and expertise. Debugging and visualization. While TensorFlow provides tools like TensorBoard for visualizing and debugging machine learning models, debugging complex TensorFlow graphs can be challenging, especially for large-scale models with many layers and operations. Improving debugging and visualization capabilities could enhance the developer experience. Deployment overhead. Deploying TensorFlow models in production environments may require additional overhead and infrastructure setup, especially for distributed computing or deployment on mobile and embedded devices. Streaming the deployment process and improving deployment tools could simplify this aspect of TensorFlow usage. Competition. TensorFlow faces strong competition from other machine learning frameworks like PyTorch, which has gained popularity for its simplicity, flexibility, and dynamic computation graph approach. TensorFlow continues to evolve and innovate to maintain its position in rapidly changing landscape of machine learning frameworks. Overall, TensorFlow is a powerful and versatile machine learning framework with a wide range of strengths, including scalability, flexibility, a rich ecosystem, and production readiness. However, it also has some weaknesses such as steep learning curve, complexity, debugging challenges, deployment overhead, and competition from other frameworks. By addressing these challenges and continuing to innovate, TensorFlow aims to remain a leading choice for machine learning and AI development. Let's look at some of the use cases for where TensorFlow excels. TensorFlow excels in a wide range of use cases across various domains, thanks to its flexibility, scalability, and extensive capabilities. Here are some notable use cases where TensorFlow shines. First is computer vision. Image classification is one of the examples where TensorFlow is widely used for image classification tasks such as identifying objects or scenes within images. It powers applications like automated image tagging, content moderation, and visual search engines. Object detection. TensorFlow's object detection API allows developers to build models for detecting and localizing multiple objects within images or video streams. It is used in applications like surveillance system, autonomous vehicles, and retail analytics. Image segmentation. TensorFlow enables semantic segmentation of images where each pixel is an image is classified into different categories. It's used in medical imaging, satellite image analysis, and video processing. Natural language processing. Text classification. TensorFlow is used for sentiment analysis, spam detection, topic classification, and other text classification tasks. It's employed in social media monitoring, customer feedback analysis, and content moderations. Another example of NLP is named entity recognition, NER. TensorFlow's sequence modeling capabilities make it suitable for NER tasks where entities like names, locations, and organizations are identified within text data. It's used in information extraction, chatbots, and text summarization. Machine translation. TensorFlow powers machine translation systems that translate text between different languages. It's used in applications like multilingual content generation, localization, and cross-cultural communication. Next, number 3 is speech recognition and generation. With speech recognition, TensorFlow is used for following tasks such as converting spoken languages into text. It's employed in virtual assistants, voice control devices, and speech-to-text translation systems. Speech synthesis. TensorFlow enables text-to-speech synthesis, where written text is converted into spoken language. It's used in voice assistants, audiobook production, and accessibility tools for visual impaired individuals. Recommendation systems. Collaborative filtering. TensorFlow is used to build recommendation systems that analyze user behavior and preferences to suggest personalized recommendations for products, movies, music, and content. It's employed in e-commerce platforms, streaming services, and social media platforms. Content-based filtering. TensorFlow enables content-based recommendation systems that recommend items based on their attributes and features. It's used in product recommendation engines, news aggregators, and job portals. Time series analysis. Forecasting. TensorFlow is used for time series forecasting tasks such as predicting future stock prices, weather conditions, or demand for products. It's employed in financial analysis, supply chain optimization, and energy consumption forecasting. Anomaly detection. TensorFlow enables anomaly detection in time series data where unusual patterns or outliers are identified. It's used in predictive maintenance, fraud detection, and network security. And finally, reinforcement learning. Game playing. TensorFlow is used for training agents to play games and learn optimal strategies through reinforcement learning. It's employed in game AI development, robotics, and autonomous systems. Control systems. TensorFlow enables the training of control systems that learn to perform tasks in dynamic environments through trial and error. It's used in robotics, industrial automation, and autonomous vehicles. These are just a few examples of diverse range of use cases where TensorFlow excels. Its versatility, scalability, and extensive capabilities make it a popular choice for building and deploying machine learning models in real-world applications across various domains.